Welcome everyone to our Tuesday webinar. We have a updated schedule for the next few weeks webinar show on the screen, and I hope you will continue to join us. As usual, if you have questions during today's talk, please submit them in the chat, and we will try to answer them at the end. The talk will also be recorded, and we will post that in the HNMTL website after the talk. Today's talk will be given by our Principal Research Engineer, Dr. Mark McCollum. Mark McCollum always wanted to be an electrical engineer. He also wanted to be a home builder and musician. All his dreams have come true. He received all of his electrical engineering degree from UIUC. He has been linked to MNTL for decades. His PhD committee included 2 people who were former director and one whom we named the building after. When not working at HMNTL, he is rebuilding his house and strumming a guitar. He has also built car radios, run a lab at NICE, built high power transistor for cell phone base station, and run a technical training and consulting company. He has also worked on international contingency risk assessment and remote positioning for tools in brain surgery. With that, let's welcome Dr. Mark McCollum.
Thanks, Edmund. Assuming everybody can hear me, we've been having a little bit of trouble. If I drop off, as soon as I reconnect, we'll get going again. Thanks for coming. So today we want to talk about vacuum systems. It's simply going to be 40 minutes, isn't very long. There was a time when I ran a training company and all of my lectures were 8 hours long. So 40 minutes seems pretty short to me. I hope it seems short to you. I had a friend who once said that it's worse to be boring than to be wrong. And any of you have spent 4 days in a row at a technical meeting, you probably believe that as well. So I'm going to give a few reminders about how to think about vacuum and then give you an introduction and a brief tour of some of my friends, namely pumps and gauges. A brief history of vacuum. Aristotle believed that vacuum would eliminate all resistance to motion, so there couldn't be a vacuum. Galileo was one of the earliest to study vacuum. He measured a force required to move a piston to be able to, essentially like a hypodermic needle, draw up water, which was used in his days to keep mining operations dry so the miners didn't drown. A colleague of Galileo's was Torricelli. He used mercury in similar experiments to Galileo. The difference is he had a tabletop laboratory because he could have a tube of mercury and found that it was 760 millimeters high, which we now call a millimeter of mercury, a torr, as a measure of pressure, where Galileo, playing with water, his closed-ended tube had to be 10 meters tall. So you had to have a pretty big laboratory to be able to do pressure studies with water. Hello? Sorry, I was told I fell off. I hope that you can still hear me. Pascal learned and experimented and demonstrated with vacuum, made one of the earliest barometers. Von Guericke is actually the beginning of many of our lives because he was the first to demonstrate vacuum in a very straightforward way. He's the one who you've perhaps seen the drawings and the pictures of taking 2 suction cups made of copper and pushing them together and showing that horses couldn't pull them apart. Actually, the beginning of many of our lives in vacuum came from Langer, who improved the diffusion pump. Before there was a diffusion pump, there was no surface science because there was no surface to look at because it was covered with an enormous number of extraneous molecules that were on the top of all surfaces. So until we could get to high vacuum with early diffusion pumps, there wasn't anything. So that earned him a Nobel Prize in chemistry. So let's remember that gases at atmospheric pressure, gas molecules are colliding with surfaces and other gas molecules. Now that may seem obvious to you, but in fact, what this feels like is about like you leaving a basketball arena or a rock concert where you're packed in trying to leave, and sometimes you don't even have control of yourself. You're so packed in, bouncing off of people. As soon as somebody opens a door near you, you just get pushed out. There is a little bit of guidance because people are trying to walk out the door, but there tends to be a equalization that takes place, even though it's not for the exact same reasons. It seems to be similar to how it works in traffic. But when you have things very close together, they collide off of each other, tend to go toward equilibrium, and they know that they have neighbors and they run into them constantly. At high vacuum, gas molecules collide only with the surfaces of your equipment. The gas molecules don't know they have neighbors. They're kind of trapped in some sort of social distancing. They don't know anybody else is even around. And so here at high vacuum, we want to think of density. So there's more than just simply atmosphere and high vacuum, but for our purposes today and our brief time together, I want you to think in terms of these two, because it's necessary for us to understand how vacuum pumps and vacuum gauges work. So we want to think the right way about pressures and variations so that we don't do silly things. Having discussions about equipment, it's easy to sometimes miss what's really going on and what the purpose is. So back to a game that you probably played in a early chemistry or physics or solid state class. If the diameter of a molecule is around 3 angstroms, then we could line up about 10 to the 7 on a centimeter ruler if we could pick them out of the air and line them up. If we close pack a cubic centimeter, we get about 10 to the 22. At atmospheric pressure, if that were a gas, say I stacked my cubic centimeter full of nitrogen molecules, if I release it into the air, it's going to expand by about 1,000 times. In fact, for nitrogen, it's probably closer to 650 or 700. So that means we're about 3 orders of magnitude down in density at atmospheric pressure than we are in a closed pack solid state. So about 10 to the 19 molecules per cubic centimeter. So where are we at 10 to the minus 5 torr? Well, that would be 8 orders of magnitude less dense than 10 to the 19. So if we want to calculate the mean free path, it's around 8 meters. And I'm guessing the way most of you probably are situated right now, you're probably in a room that's smaller than that 25 foot, which means if that were a vacuum chamber that you're in right now at 10 to the minus 5, no matter how much you bounce around the room, you're probably never going to run into anybody else, which may be the way you feel these days. If we extend that 10 to the minus torr, an easy to achieve ultra high vacuum type of number, the mean free path is 30 miles, which would be a pretty big vacuum chamber. So the collisions are only with the chamber and the equipment, not with any other gases. This changes the dynamics and what's going on inside of our chamber a great deal compared to when we're at atmospheric pressure. So how do we think about vacuum? Well, near atmosphere, we think in terms of small mean free paths. The gas molecules know they have neighbors. Below about 10 millitorr, we think about density. At that level, the gas molecules have large mean free paths. All the gas molecules think they're alone. So our full range of vacuum is really pretty astounding. It's 15 orders of magnitude. from about 760 torr if you're visiting the beach, up to almost 10 to the minus 12. And we might ask, is that really a reasonable range? How much of that range do we use in the semiconductor industry? And the answer is most of it, from subatmospheric CVD down to some of the very high vacuum used in surface science metrology tools. We use most of this 15 orders of magnitude. In street talk, people sometimes talk about reduced pressure, low vac, high vac, UHV, which stands for ultra high vacuum. If this isn't something you're familiar with, there's actually implications I just want to point you to. We don't have time to go into it today. We might talk about some of the hardware and plumbing issues related to laboratories. But I do want you to understand that each of these types of words that people will speak about implies a whole set of hardware and management and types of pumps and gauges. So at low vac, you might even have plastic parts, perhaps a lot of ceramic parts. When you get to high vac, you're going to start to have mostly metal parts with high quality O-ring seals. And when you get to ultra high vacuum, typically this implies mostly stainless steel with metal seals. So it may seem sloppy, but sometimes it's actually implying specific parts. So let's just mention one of our common friends in vacuum, because you build your system and at some point it's probably an air. And air is made up of this mixture of gases, more or less, around the planet. And the problem is that's dry air, and that never happens in central Illinois. So in fact, it's this, but it's all reduced by about 2 to 3% water. Now, water is fairly sticky, and at room temperature, we tend to think of it as a liquid, where these other, even though they all have vapor pressures, these other items tend to be gases. So when I take my new system, or even one that I've just vented to air to take my sample out of, I expose it to this air that has 2 to 3% water in it. And as I pump it down and rough it down most of the way, very quickly, almost all of the gas inside my chamber is now water, which is something to be aware of, because it's a contaminant that's hard to get rid of in vacuum chambers. So what are you pumping out of your chamber? It turns out the first challenge you have is getting the water out. By the way, just as a maybe overstated, maybe even silly comment, what are the other sources of materials in your chamber? When you're getting down to high vacuum, we have so few molecules. We actually could run into a number of things that could be in our chamber. So the hint is pretty much anything, and sometimes chasing down where these things come from can be quite a challenge. So let's remind ourselves the behaviors of pumps. This is not really intuitive if you haven't thought about it. Hopefully this will make it clear, but this is an appreciation. I hope you can gear shift in your mind depending on the type of equipment you're using. So viscous pumping, you suck. You have a chamber and all of the molecules know they have neighbors, they're bumping into them. And I simply draw material out with some mechanical method. Maybe I grab on a handful of these things. If I were to think of this as a swimming pool, I could just reach in with a handful of water and throw it out into the grass, and I've now pumped water out of the pool. If I want to pump harder, then I get a bigger pump, and I suck harder, and I can now pump faster. When I get into the molecular regime, that's all gone. You can't suck because none of the molecules know they have any friends. So now the molecules are bouncing off, and you'll notice that I've drawn some sort of random path maybe that a molecule of gas has to do moving through. Please don't miss that there's no specular reflection coming off of the sides of your chambers. And that's because the molecules see the molecular shape of the walls, so they tend to come off at some sort of cosine function, not too unlike a Knudsen cell. So The only way I can pump at molecular pumping speed is to wait until the molecule goes through the hole, the throat, the connection to my pump. So I can buy a bigger pump, but I won't get additional pumping. The only way to get more pumping in a molecular regime at high vacuum is to cut a bigger hole in the side of the chamber, which means then I can get a bigger pump. So when I'm doing molecular pumping, then everything is probabilistic. So it's the probability that the molecule goes into the pump and doesn't come back into the chamber times the probability that it actually finds its way out of the side of the chamber. As a very quick example, the reality of this probability is handled in some simplistic induction numbers. So if I simply take an 8-inch cryo pump that is rated at 2,200 liters per second, and then I connect it to my chamber, and just typically I want to have a valve to be able to isolate that cryo pump because I might want to vent the chamber, put in a sample, rough it down, and then open it back to vacuum to pump it down with the cryo pump. So something that's just 5-6 inches thick, like a gate valve, has a conductance number, and you calculate your effective conductance by adding the reciprocals of these. So in fact, my net pumping at a chamber that's just a couple inches away from my pump, because of the probabilities of the molecules bouncing around and bouncing back into the chamber, is high enough that I lose quite a bit of my pumping speed just from something short. If you start talking about a tube that's 5, 6, 8 inches long, or an elbow, you very likely have lost 80 or 90% of the pumping speed that you purchased. All right, so let's talk briefly about what are our pumps that are available to us, and then we'll talk about gauges. So there's essentially 3 different types of pumps. There's positive displacement pumps. That's grab and remove, essentially. Like I said, I could grab a handful of water out of my swimming pool and throw it into the grass. Now it's not in the pool anymore, so I would say that I've pumped it. There's momentum transfer. This is where I'm going to bang into, I'm going to swat at, hit, move in some way, my molecules out of my chamber. So in fact, in my swimming pool example, I could just stand by the side of the pool and I could splash sideways with my arm and knock water out into the grass. Now I'd have it out of the pool. That would be momentum transfer. And then entrapment, what I'm going to do is stick it somewhere in my chamber. So it's not gone, it's still in my chamber. So this would be kind of like taking a glass of water out of my pool and then putting it in my favorite floaty toy that I might have a drink holder in. So now it's not in the pool because it's in the glass. So this is the 3 ways that we say we pump. Well, be clear and notice that the first 2, we actually remove gas from the chamber. So if we're running a complex process with a great deal of gas flow through the chamber, I probably want to use a positive displacement or a momentum transfer pump because I want to get that gas out of there. If it's toxic gases or dangerous gases, corrosive gases, or some particular type of material, I really like 1 and 2 because I want to move them into a scrubber so that I can abate the situation well. Entrapment pumps are going to hold the material temporarily inside my chamber somewhere, and that there might be certain types of chemistry that I really don't want to store because they represent a potential disaster later. You can see from this, I'm not going to read this to you, but there's a wide variety of pumps at a wide variety of ranges here. So let's talk about some of the most popular ones. So positive displacement. It sounds like a lot of words, but what we're saying is we're actually going to grab and move some of this. Because it has to do with grabbing and moving, it's very hard to grab a molecule some way and take it out of the chamber. So there are no molecular pumps that are positive displacement. These are all viscous pumps. So let's give a quick explanation of how a diaphragm, rotary vane, screw, roots, and scroll, very popular pumps, how they work. So in a diaphragm pump, this might be similar to an aquarium pump if you keep fish. What you have is a couple of check valves, one that goes in and one that goes out. This could be a flap valve, it could be a ball that moves up and down. But if I have this purple thing at the bottom as my diaphragm, and I'm able to grab onto it and move it to expand the volume in a vessel, then the gas goes in one of the check valves. And then when I switch it around in the exhaust function, I push that in. I decrease the volume inside of my pump. I seal off this red valve, if you will, open the blue one, and it blows out. So I could connect tubing to this. And this is a very popular pump that is used for many things in many formations. And the biggest hazard is if the diaphragm breaks, then now you have your chamber and your gases open to atmosphere, which is kind of makes them a poor choice for dangerous materials and specialty chambers that can't be suddenly vented to air. So I have a cartoon here that I was able to find. It'll give a demonstration of a 2-channel diaphragm pump operating here. I hope that that video is good enough for you to see over the miles. I'll play it again. So you can see the balls are check valves, and there's 2 diaphragms that are opposed to one another. So this is essentially almost like a full wave rectifier. It's pulling on one side or on the other. Very long term, these things have been around forever. They're still made similarly to how they were many decades ago. Rotaryvane pump, both versions that are oil sealed around the edges here, well, as well as dry pumps. So what happens is these rotate. So what I've drawn here is a 2-stage pump. If you can imagine this inner circle rotating and this green funny thing being a spring, pushing these vanes out so they seal around the larger circle, then the gas flows around as these things spin, and multi-stages of these can be very high quality pumps and get you to pretty good vacuum. It is good to switch over to a high vac pump. And I have a motion demonstration for you here. Very nice computer drawing. You can see how the vane moves and allows it to open up these valves up at the top, and how a rotary vane works. Screw pump. A screw pump essentially works very similarly to a grain auger. You know how a screw works. If you turn it, it goes into maybe a piece of wood or something. If I hold it still and seal it at the edges and can have each of the edges sealed, then I can have an input. This particular case on this cartoon, the gas input is here on the top right, and the flow is to your left, and the exhaust is here. So if this spins, it moves material. You can, especially nowadays with the ability to manufacture a very complex material and to draw them on CAD, they sometimes have 2 and more screws. In this particular case, the gas in and out on a dual screw pump. And I have an excellent cartoon. Typically, we like BCL3 and other type of inputs. We don't usually in our etch tools use olives, but it makes a great video to see how it works. We also don't use sausage very often in most of our equipment, but you can see how a screw can easily pump and move all sorts of things, even beyond our interest in semiconductor processing. Come on, you have to love a screw pump moving sausage. A roots blower, a lot of people have a hard time understanding what its purpose, and that is because it's a little bit odd. A roots pump doesn't work by itself. That's why sometimes it's referred to as a blower or a roots blower. So these are very carefully long shafts with lobes. You can see them inside of this cutaway. And sometimes there are 2, there are some that have 3. And these rotate, so the gas coming in will go around the outside, both on the left and on the right, as these spin very fast. So you can see there's not a huge amount of compression, they just push. So they end up kind of acting like a fan. So a roots pump is typically installed to get extra boost and movement in mid pressures, not molecular, of course, but at the lower end of viscous flow, they work very well. So they're usually placed for high gas throughput between a mechanical pump and a high vacuum pump that moves gases through. So here's a nice video so you can picture how this moves. And of course, it pumps magic blue dots. And I'll play it one more time because that one's just fun to watch. Scroll pumps have become more popular. I think there's ease in manufacturing them, but they seal well, they work well, and even in slightly dangerous environments, they still work well. They last a long time between rebuilds. And what they do is they have two coils that are nearly identical, and one of these coils is attached to the back plate you see, and kind of in this shadowy blue here, if you can imagine that the other plate is attached on the other side, and then where the coils and the flat surfaces below touch, they're sealed with an elastomer that goes into a groove in the edge of the coil. So this is how they move. I think by watching this, you can imagine that if they seal on their faces and they seal down on the edges, where that seal is called a tip seal. I'll play it again, but if you, and it turns out this mechanism is fairly reliable. The pump slightly shakes because there's quite a bit of momentum transfer, but these last sometimes more than years. And if you catch the tip seal before the metal rubs against itself, these can sustain a simple rebuild several times. And the rebuild is nothing more than you can see here. It's the removal of this tip seal, and there's some other items and some lubrication to put inside. But I'll play that again. That tip seal, you can see the person here is just pulling that out. You replace that, and anyway, these can be rebuilt in just a couple of hours and be put back into service quite nicely. All right, next set of pumps, momentum transfer pumps. For viscous, the example I'm going to give is a Venturi. It's commonly used to vent things like gas cabinets because it also launches the gas pretty well and can be sent into an abatement system if it's a particularly concerning gas. And then in the molecular range, our favorite old diffusion pump, which created surface science. We don't use mercury in these anymore. We use oil. We can use oil to hit molecules and knock them to the bottom of the diffusion pump. Or in the case of a turbo pump, which is a common slang for turbomolecular pump, we're going to have somebody sit around with baseball bats whacking at molecules to knock them down into the bottom of the pump. They're actually blades. So we'll show what these are. So these are momentum transfer. I'm going to hit the gas to get them to concentrate someplace, and then I'm going to likely, in the case of molecular flow, I will need to remove them with some sort of viscous pump after that. So a Venturi is a carefully designed plumbing part that I put a huge flow in this direction, and that movement causes a vacuum to form. And so you get a pressure reduction right here where I'm pointing, and you can pull it in from another direction. So these can work very well, but to drive them, it takes an enormous flow of gas. Here's a cutaway of a turbomolecular pump. If we remove the housing here at the top of the pump here on the left in the blue, then it looks like what's on the right. What I want you to notice, hopefully the resolution is good enough for you to see, is that the angle of these paddles is different as it goes down through. Some of these paddles are stationary, so they're referred to as stators. There are some other spacers that are in there. And all of this is both modeled and measured probabilistic happening. So remember, the molecular shape of what's going on with these paddles means that if it hits a gas molecule, it tends to come off in some sort of cosine function probabilistically. So I want to have a reasonable chance if a gas molecule wanders in the molecular activity down and hits one of these blades, that there's some higher probability that it goes down rather than up. And I hope that for each layer this happens, so the gas gets concentrated down in the bottom, and then we can connect some sort of viscous pump off on the roughing port on this pump. And so I can have high amounts of gas flow moving down through this pump at high pressures. I'm sorry, at molecular levels at low pressures. All right, so I was able to find a nice video. You can see our magic green dots sometimes are getting hit and moved down. So we're trying to capture gas molecules that are moving at higher than 1,000 miles an hour. So to increase our probability of hitting them and knocking them down through here, we benefit by having these blades moving at better than 1,000 miles an hour. So in fact, that suggests that turbomolecular pumps work best if we spin them at fairly high speeds. And typical speeds of rotation on turbomolecular pumps will be something in the range of 30 to 60,000 RPM, so that it has a chance of hitting the baseballs that are being pitched at it at 1,000 miles an hour or more. Diffusion pumps are wonderful for several reasons. One, they can be purchased to be huge. They allow for huge amounts of gas flow. They don't have gas getting trapped in them because they're hot. The downside is you've got a whole bunch of hot oil. So if you ever spoil molecular flow or spoil your vacuum, then suddenly you have a large vacuum jar with a pot of boiling oil in it. So they can be very disaster prone. So I have a cutaway here on the left. On the right, I've tried to draw a schematic. So it's essentially a deep bowl with these conic sections that when the vapor transfers from the hot oil going up, they are shot downward. So you end up with these types of jets. So my process chamber is above, and my 4-line pump, some sort of displacement pump, is going to be here. But I can move huge amounts of gas flow through here, and I can purchase for a fairly small amount an enormous pumping speed. But with the hazard of backstreaming oil, which isn't pleasant for any time you need very high vacuum, and also a potential disaster of putting all of this oil inside of your chamber. So it kind of shoots like that, almost like behavior, almost like a coffee percolator, where there's a downward force that any molecules that venture in from the top can be knocked downward by the oil, and then they hit the side of the pump, which you can see in the cutaway on the left. These ridges are cooling lines, so the outside has to condense the oil so it drips back down onto the heater and continues to recycle. All right, I have a lovely dramatic cartoon drawing here of, there's the heater in the bottom. This is the cutaway diffusion pump. So that's the oil vapors moving up through these carefully made cones, and you can see then that the vapor stream of oil shoots downward, and then any molecules that happen to wander into the top get knocked down and concentrated to the bottom, and then we pull that out with a mechanical pump. The blue is indicating that there is cooling so that the oil condenses on the sidewalls and eventually drips back down in the bottom. Popular oil that's used is Sanovac 5, which was developed for ultra high temperature gearbox oil in fighter jets. All right, our third and last types of pumps are entrapment pumps. So if I have molecules bouncing around in my chamber and I want less of them, if I can get them to stay someplace, then they aren't bouncing around in my chamber. So I say that they're pumped, but I'm still holding on to them. And there's a sorption pump that is a very clean way of roughing high vacuum chambers. So it's a viscous entrapment pump. And molecular includes cryogenic, Gettering, and ion. So let's move through these. Sorption pumps I don't see very often, but they were very popular for pumping down MBE systems, which you don't do very often. And these have no oil, they make no noise, they're icky because you have to collect a lot of liquid nitrogen. So you simply have a vessel that you fill up with as much high surface area ceramic as you can. And this stuff tends to freeze out things that will freeze at liquid nitrogen temperature. So if I have 3 of these, for example, sometimes you can get away with 2. I open the valve, say on section number 1, my blue fade here is liquid nitrogen. So I now have cold zeolite, and water vapor and air will freeze in here. And so I open this until I get to the lowest vacuum I can, and then I close this valve, I move on to the second, then I close the valve, and then I move on to the third. So I can get down to pretty low vacuums where I could even use this as the only roughing pump for an ion pump, which we haven't gotten to yet, but doesn't have much pumping capability. But this works very well, but it's time consuming. A cryo pump is similar to a sorption pump, except instead of having liquid nitrogen temperature and surface area provided by zeolite, I now have nickel-plated condensing array up at the surface that will freeze out water. So very similar to liquid nitrogen temperatures, but then I also have an array. I do that on purpose. It's called regeneration, but I want to do it through a valve that's somewhere else. A simple Gettering pump, turns out titanium is highly reactive. So if I put some pulses of high voltage through a titanium filament and let some fresh titanium in a nice vacuum evaporate onto a surface, then any molecule that hits that has some reasonable probability of being adsorbed onto the surface. So that's going to be chemisorbed onto the fresh titanium. So you typically turn this on when you want to drive some extra contaminant out of your chamber. Now, one of these on steroids with a whole lot more to it is a sputter ion pump. These have terrible pumping speeds, very low. They're very heavy. They're awkward. They're expensive. They have high voltage supplies, but they're wonderful if you have a zero gas load. So something like a metrology tool or e-beam lithography, they work nicely because they're all so quiet. So here I have a cylinder anode, I have titanium cathodes, and I can, in this permanent magnet, get these to coil and spin through free space, and then they whack into the titanium cathode, where they can sputter off some titanium, which gives me some fresh titanium around this region, which acts like my sublimation pump that we just talked about. Or they can also hit and be implanted into the titanium. So I have both physisorption and chemisorption, and like I say, small pumping, but very clean, quiet. They have some very important places that people like them. All right, very quickly, let's go through vacuum gauges. You can imagine if I'm going through 15 orders of magnitude, I I've got quite a challenge of figuring out how many molecules are there, especially when I'm at very high vacuum. A Bourdon gauge is a mechanical distortion gauge. I can take a coil of a tube and attach a dial on it, and as this fills up, it will tend to try to become straight, and I could make this a dial. I can have a point here go back and forth so I can see it next to a ruler or something. They're clunky, but you still see them sometimes. More commonly used nowadays, we can have excellent electronics that can help linearize and take care of any problem here. But a capacitance manometer works very well. So if you look here that I've labeled flex plate, this red diaphragm is completely sealing between pressure 1 and pressure 2. If I put another plate and electronically measure the capacitance between these two, I can accurately measure the distance, and I can transfer that to the pressure difference between 1 and 2. So this works very well. You can see it has an enormous range all the way to the -5s to atmospheric pressure. So these are very popular gauges for pump down areas. Thermocouple gauges have been around for many years. There's several versions, this one and the next one that has a different name, but an ordinary thermocouple gauge, I drive some current through a heater, and that heater doesn't have any conduction if there are no molecules around. So it actually gives off more energy as the pressure is higher, and as it gets lower in pressure, it gets warmer. And so I can measure its temperature. That's why it's called a thermocouple gauge. And I'm measuring the cooling that's provided by the gas molecules around. It also has a fairly wide range. It doesn't go out to atmosphere, but it can be used for a mid-range gauge. And for some simple, inexpensive, not too high of a vacuum, often you'll simply have this type of a gauge, and you wait to rough down until you're down into the millitorr range before you turn on the thermocouple. One that's a little more accurate and sensitive is a Pirani gauge. It's similar, but we arrange our heaters and resistances into a Wheatstone bridge arrangement, and I can measure my thermal conductivity better. So it has better linearity and stability than a simple, inexpensive temperature gauge, and the price typically matches its improvement. A little lower range, but a little better behavior. One of my favorite gauges is the cold cathode gauge because there's no filament to burn out, so it doesn't burn out. So electrons or and ionized gas molecules give rise to a small current between a high voltage anode and cathode. But the trouble is I have to get something charged and moving and spinning so it does some ionization of the gas molecules. So if you're at very high vacuum, you can't get the cold cathode gauge to start. So it's its problem. So it works best in an automated system that turns it on at a lower vacuum so that it can stay on at higher vacuum. But when that happens, it has a very broad range and can be an excellent thing that doesn't burn out. And then you can wait to turn on your hot cathode gauge when you get to higher vacuum. A hot cathode gauge has been around for years, very popular, reasonably repeatable. Now I have a similar thing to my cold cathode gauge, except I supply electrons boiling off a hot filament to ionize the gas so that I can collect a current between a collector and my cage. And this is pretty good all the way down into the 10s and the 11s range for Torr. Just as a mention, if you're wondering how do we know what we know, I spent 5 years running a lab at NIST, so I'm always interested in whether or not anybody knows anything or they're just measuring something they wish, it's wishful thinking. What has been used for vacuum standard is a spinning rotor gauge. This is a magnetically levitated 4.5 millimeter steel ball, and you measure the deceleration that comes from gases hitting the ball. Yeah, this would be terrible to try to use. The Response times are not very good. And if you notice the range, just something to think about, the range is only in the mid to high vac. So anything we're extending and saying that we know down into 10 to the minus 10, 11, 12, knowing exactly what that vacuum is, gets pretty philosophical. If somebody tells me that their high vacuum chamber is at 2 times 10 to the minus 11, and someone else tells me theirs is at 4 times 10 to the minus 11 torr, I don't consider them to be at different pressures. All right, so we talked a little bit about thinking about vacuum, gave a tour of pumps, a tour of gauges. So my conclusion is, if you have any issues with a vacuum chamber, whether it's yours or mine, if I can be of any help, or any of the MNTL engineers can be of any help, we'd be happy to. And in this grand Corona time we live in, if you want to have a discussion, I'm glad to have a talk with you about any equipment that you're struggling with, or building or designing. Be happy to help in any way I can.
All right, thank you, Mark. I actually got a question. So could you comment on why we care about vacuum? Why we care about how good a vacuum we have in a typical clean room tool, such as evaporator, etcher? Why do we want to have good vacuum? Could you comment on those?
Yeah, and could go on for hours. So one of the first practical thing that came out of vacuum was there was a graduate student who had played with vacuum, and he joined up with a guy you may have heard of. Edison was having trouble with his filaments burning out as he was trying to make an electricity-driven light bulb. And it was actually putting this into a vacuum that helped the lifetime. So in that case, it was to reduce the gases that were reacting with it, particularly oxygen, oxidizing the filament and having them burn out. So this is an important issue with any of our metals deposition or other materials. If I want to heat up a metal, get it hot enough that it is evaporating, I don't want it to run into any oxygen on the way to my substrate, or I'm going to have a metal that's actually an oxide. In fact, this is done on purpose in reactive sputtering, where you oxidize the metal on purpose while you're putting down a dielectric. So the reason we want vacuum is to remove other things for chemical reasons. In the case of most of the tools we have at MNTL, many of them were lighting up a plasma, so that we have to be able to control the density of the atoms in the plasma. Because of the radio frequency loss, we won't be able to maintain a plasma. And the reason generically that we're creating a plasma in a plasma-driven tool is to add energy for chemical reactions, either etch or a reaction for deposition, without doing it only with temperature, so that our substrates can be at a lower temperature. It also allows chemistry that doesn't take place at other pressures. So one other reason that's important to remember is, as I lower the pressure in a gas reaction, I decrease the thickness of the boundary layer at the surface of my reaction. So I can control boundary layers, and these can become stagnant. They can become impoverished of the rich material I need for, say, growing an epi. So controlling that boundary layer, that's the interface between my incoming chemical species and my reactions at the surface. So those are the main reasons: is removal of gases, boundary layer control, and RF energy involvement control for plasma.
Thank you. The next question we have is, what is a good rule of thumb for spacing between a turbo pump and a roughing pump? Let's say we have a 1-inch tube between them. Is it good? And how far apart they should be between the 4-line pump and the and the turbo pump?
Yeah, so there's several things going on there. Not being asked is I want my turbo pump as close to the chamber as I can be, as the example I gave. Otherwise, I effectively lose a great deal of pumping speed. But when I connect my turbo pump to my mechanical pump, I would like them to be directly adjacent so I don't lose any of the flow or drag things down. And this is not the same as the molecular issue. This has to do with conductance and moving gases. Also, many of the materials we have give off, they're rich in unreacted materials, so they're going to plate out someplace. And it's bad to have too long of a line where you're going to plate out material that may be difficult or dangerous to clean up later. However, there's some advantage of moving the mechanical pump far away from the turbo pump, because maybe you would like that pump to be closer to your scrubbing equipment, and perhaps it's in the basement or in an adjacent room. And if that happens and it impedes maybe the absolute pressure you can get in your vacuum pump, because in your reaction chamber, because your mechanical pump is so far from your turbo pump, that's an ideal place to try to make that four-line a higher diameter, or to add a roots blower, which will boost the throughput through your four-line. Four-line's sometimes vague, but it refers to the plumbing that is between your high vacuum pump and your mechanical pump.
Yeah, so next question is, since the scroll pump, screw pump, and Rotaryvane pump all have the same roughing vacuum range, is there any reason to choose one over the other?
The primary reason probably has to do with cost. And that would not be just the price tag, although that's awfully tempting when you're trying to set up a new experiment or create a new system. But you also need to think in terms of the long-term cost of ownership, much more of an issue in production than in much of what we do. But if I'm going to tend to lean toward a scroll pump because of the ease and simplicity of rebuilding it. Sometimes it has to do with history. I've actually never used a screw pump, so I'm more comfortable with the things that I've rebuilt and worked with before.
All right. How about the high vacuum? Is there any pros and cons that you can comment on whether we should use the turbo molecular pump or cryo pump or ion pump? Is there any different application that require different pump?
Sure. So an ion pump is a terrible beast because of the high voltage, the expense, and the weight. And it has no pumping speed. And you say, well, why would you use it? And the answer is it's completely clean. And if you have a closed system, it can be a nice choice. It also has no noise. So for things like microscopes, if there's no real gas load to them, they're wonderful. If you're sitting there working on that all day, having a quiet room and having no moving parts, except the fields that are generating ions and causing sputtering. In that particular case, it's a wonderful choice. The next case, typically in the types of equipment we're dealing with, is whether or not there's a large gas load. If there's much of a gas load, you probably don't want a cryo pump because you have to regenerate it, which is the action of shutting down your system, closing the large mouth gate valve, letting it fully heat up to room temperature, which is usually assisted with some warmed nitrogen, and getting rid of all of the material that you've trapped in there and getting rid of. So I know people who have used them for higher gas loads, but it implied that after every run they have to regenerate it, which is typically an overnight affair. It's certainly at least 4 hours. So the choice of other pumps then between a cryo and a turbo for most people these days is whether or not gas is moving through it. So if I'm going to be moving gas, say in an etch tool or a deposition tool, I'm going to tend to choose a turbomolecular pump because it's a throughput pump rather than an entrapment pump. So I can move all of my unreacted waste through the pump and into a scrubber, and the only dangerous materials that I have in my facility is in the operating tool, and then when I'm all done, it's all gone and I haven't trapped it in a cryo pump. So it has to do with your choice of pumping speed and whether or not you have a large gas load are the main issues.
All right. Thank you, Mark, and thank you everyone for joining us today. Hope you will join us again next Tuesday. Thank you.